I'm very happy this is the last lecture. So before talking about the future, i.e. this upcoming lecture, let me remind you what we did last time. So the goal and the central point of last lecture was to introduce the definition of hierarchically hyperbolic space and hierarchically hyperbolic groups, which now I will recall very, very briefly. So a hierarchically hyperbolic space consists of the following. So first of all, we need to have a space, this is a quasi-geodesic metric space. And then we have a set S of delta hyperbolic spaces that we can think as coordinates, and those are called domains. Okay, and then those hyperbolic spaces are arranged having three mutually exclusive relations. First is called nesting, and this means one is inside the other, is inside the other, and this is a partial order with a single maximal element. Then is orthogonality, which means product. All of those are in quotation marks because they don't exactly mean these. This is what morally they means. And then transversality, which means arranged in a tree-like way. Arranged like a tree. Okay, so we had those three relations, and then we had projections. There were two kinds of projection. First, there was the projection pi u from my space to the hyperbolic space associated to some domain u. And then, so what does it mean? So let's recall ourselves. For instance, if this is the big space, then in the example we had before, a domain u could be this vertical space associated to a flat. And then the projection, I just take a point in my big space, and then I project closest point projection over here. Good. This is how this projection looked like. And then we had another type of projection, which we call them rho. And then we say rho from u to v, where u and v needs to be in S, and those are can be of several types. So if u is the projection from u to v, so u needs to be the big one. So if v is inside u, this is a projection. V is inside u from u to v, from cu to cv. And what is the idea? So the only space which is above other in this example was the infinite valence tree obtained by collapsing all the flats. And then, for instance, let's say I want to project on VA, I want to project from T to VA. So this is going to go from the space T, which is this one, to the space VA, which is that line. Let's say that I want to project this point here. This point is going to correspond to a flat, let's say this one. And then the let's do it another color. This flat, and then the projection is going to be the closest point projection. So again, well, in this particular case, it's going to be exactly the one as before. So this is how this map is defined. And then this is one case. The other case, if now u is inside v. So what does it mean? I have v here, I have u inside, and then the projection from u to v is just this point. So projection from u to v. And so here, the projection from VA to T, let's say that VA was inside this flat alpha, and alpha was represented by this, then the projection would just be this point. This is where this line lives. Okay. No, I cannot go backwards. Okay, my thing blocked. Ah, no, it did not block. And then the last type of projection, where that if V and U are transverse, so they are arranged in a tree-like way, this is V and this is U, then it means that there is some sort of corridor between them. And then the projection is just this whole V projects at the end of the corridor, and this that we call the projection from V to U. So this is just a point or a bounded diameter set. Okay, so probably this was very fast, but hopefully we saw this yesterday. So this is basically what we need. And then there are a bunch of axioms that needs to be satisfied to verify that all of those things behave and are related in the correct way. But this is what you need to somehow define. This is the thing that need to be defined, and then you just need to verify that they satisfy some properties. Okay, so this is the definition. Actually, I don't know why I put it here, just so that we can see it again, because it's very pretty. Okay, so now let's talk about hierarchically hyperbolic groups. Again, let's recall that a group G is a hierarchically hyperbolic group if we need some condition. The first one is that the Cayley graph, and I always mean with respect to a finite generating set, is an HHS itself. Then we need that the group G acts on the set of domains. So what does it mean that the group acts? It means that for each small g in G, we induce a map that we just denote in this way, which is just a bijection of this set. So this is what acting on a set mean, just nothing more. But we want that this map preserves the various relations. Okay, so this is one requirement. And then the other requirement is that, okay, so we have an action. So let's say that some small g in G sends some domain U to some domain V. Then we want to have also a map associated to the level of hyperbolic spaces. So we need to have a map from CU to CV, and this map needs to be an isometry. And then we need those diagrams to commute. And those diagrams, what do they mean? They basically mean that things are compatible. So if I have the group G, and then it's the same if I first project to a space and then I apply the isometry associated to the element G, or I first act on the group via G and then project. Those two things are going to be the same. And similarly, if I have CV and CW for which rho from VW is defined, then first going from CV to CGV, or then going from CV. So this diagram commutes. This is, you all know what commuting a diagram means. It means that those two things are that you can do in the order you want. Okay, so this was enough from the recall. So what are we going to talk today? So today, the goal of today is to talk about uniform exponential growth. And everything I'm going to tell you is joint work with Caroline Abbott and Thomas Ing. So you can probably guess that this one is Caroline Abbott and this is Thomas Ing. And as I said, the goal of today is not really to prove uniform exponential growth, although I think it's an interesting result. The goal is to try to get a little bit of familiarity with some techniques that we have. Okay. Also, I need to tell you something. So at least the beginning of the talk is going to be, I'm going to basically just use slides I prepared for another talk. So this is an experiment. So the style is going to be slightly different. So there is going to be more text on the slides than before. So since I'm going to give other talks in my life, I would really appreciate if you can tell me at the end if this was better, worse, or exactly the same as the other lectures. Okay? Very good. So growth. What is the growth function? So we have a group, and then we fix a Cayley graph. And then the growth is a function that associates to a number n the size of the ball of radius n in this particular Cayley graph. So for example, if we take the Cayley graph of Z with the standard generators, then the growth of 1, so the image GR1 is 3. So there are 3 elements in the ball of radius 1. Very good. If we take the ball of radius 2, it's 5. Very good. Excellent. But these change if we change generating set. If now I take the Cayley graph of Z with respect generated by plus minus 2 and plus minus 3, the ball of radius 1 is going to be this thing, right? Because both minus 3, minus 2, 2 and 3 are connected by 0 to 0 by an edge. And so this function is going to, the value is going to be 5. If now I look at the value 2, it's going to be 13. I don't have the whole Cayley graph, just trust me. If you get very bored, you can just compute all the growth function for this group. It's not very interesting. But so the growth does depend on the generating set. This is kind of not very nice, but the important part is that the asymptotic does not. So as the two functions, well, I just add the very first two values, so we cannot really extrapolate anything, but you can probably believe that those grow linearly. So no matter which generating set I take, the growth in that case is going to be linear. And so we can make a definition. G as exponential growth is the growth of G is asymptotically exponential for every finite generating set. Of course, we only need to consider finite generating sets. Otherwise, it could be much weirder. But we just say that this function is an exponential function. Okay, very good. This makes sense, and this does not depend on the generating set. So it makes sense to say that a group has exponential growth. Now the question is, how do we compute the growth? Well, there are several techniques. A simple one is we need to contain a free semigroup. So a free group, it also suffices a semigroup. A semigroup, you can think of something like a monoid. So it's a group that generated, let's say, generated by two elements, but without the inverses, so only positive powers. And having a free semigroup implies exponential growth. The reason is that this thing is very big. And it is so big that you just need exponential space to fit it inside. It doesn't matter how distorted it is, there is just simply not enough space. You need to grow exponentially, otherwise you cannot fit this subgroup. So if you can find a free semigroup, then you have exponential growth. Okay, and there are several ways, let's go one back. There are several ways to find free semigroup, and those are usually associated to negative curvature. So if you have negative curvature, usually you can use some techniques. So for instance, if you have, so for instance, it is sufficient to have a hyperbolically embedded subgroup. So having a proper hyperbolically embedded subgroup is the same of being acylindrically hyperbolic. So this is saying that all acylindrically hyperbolic groups have uniform exponential growth, have exponential growth. This is nice. There are plenty of other classes that have exponential growth, and all the arguments at the core rely on Pingpong lemma. There are several versions of the Pingpong lemma give free semigroups. Okay, so this is how usually we prove exponential growth, by finding semigroups using Pingpong. And what is the Pingpong lemma? So I think that most of you know what is the Pingpong lemma. But the Pingpong lemma is so important and so easy to prove that I'm going to prove it for you, because it's just very nice. So if you know it, you can just zoom off, and then I'm going to call you when I'm moving forward to the next thing. So there are several versions of the Pingpong lemma. Here is one. There are a lot of other variations. So let G be a group acting on a set X. Suppose that there are elements A and B in G of infinite order, and then sets Y1 and Y2 in X, disjoint. So in particular, they both need to be non-empty. Non-empty. Such that for all n which are non-zero, A to the n applied to Y1 stays inside Y2, and B to the n applied to Y2 stays inside Y1. Then AB is a free subgroup. How do we prove it? Well, the proof is actually very, very simple. So our goal is to take a word, let's say A and 1, B, M, 1, dot, 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 A and K, B, M, K, and let's assume that this is not all trivial, so some of the Ni and Mi are different than 0. And we need to show that this is not the trivial element. Very good. So how do we do? First, let's assume that the word has the following form, has the form N1 BM1 dot 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 BMK minus 1 A N K. Okay, so the word starts with an A of some power and ends with an A of some power. Now we need to show that this word is non-trivial. So let's see what this word does to the set Y1. Well, first, A and K to Y1 by hypothesis lives inside Y2. But now, P of Y2 by hypothesis lives inside Y1. Dot, 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 dot. So this again, this whole thing is going to be inside y1, and this whole thing is going to be inside y2. So this word sends y1 inside y2. In particular, it cannot be a trivial element. Very simple. And now what do we do for the other case? Well, so suppose that we have a word, let's call it G, which is the form A and 1, B and 1 up to A and K, B and K. How do we deal with this fact? The trick is not going to work again. Well, but kind of, right? We can conjugate by A and 1, or maybe the inverse, depending on your conjugation. How do you say? What do you mean with conjugation? And then we obtain the following word. We obtain A, 2 and 1, B and 1, dot, 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 B and K, A to the minus N1. And now this word.
Sorry, did you want the second, did you want G to be different? Is it not?
So
like...
the first one, so I hope I did not make any mistake. The first one starts with A and ends with A. And this one starts with A and ends with B.
Okay, I'm sorry. Thank you.
And now I just conjugate such that it starts with A and ends with A again.
Okay, thanks. Yeah.
And now these, let's call this word G1, and then G1 is non-1 because of the previous point. And since it is conjugate to G, you cannot have something which is non-trivial conjugate to the trivial element. So G is non-trivial. Done. So this is a very simple proof. This is a very simple argument, but it's very nice. Okay, so now the Pingpong lemma is over. So I promised I would call you after the Pingpong lemma. Now it's a moment. Good. So the Pingpong lemma allows us to find free semigroups. So the Pingpong lemma is what we use to prove exponential growth. And this is to say that to some extent, of course, there are plenty of open questions, but to some extent, we do understand exponential growth. Showing that groups have exponential growth is more or less easy. But the problem, or at least a fact, this is just a fact of life, the growth does depend on the generating set. This is just a function that depends on the generating set. Can we obtain some result that does not depend on it? And this is the motivation of having uniform exponential growth. So a group has uniform exponential growth if there exists an exponential function such that this function is a lower bound for the growth regardless of the generating set, of course, as long as it is finite. So no matter which generating set you choose, there is a function that is always going to bound your growth. So your growth is always bigger than that function. This is what we call uniform exponential growth. Checking for uniform exponential growth is harder because you have to consider all generating sets. And Pingpong lemma are good, but sometimes there are some constants that go in interplay, and you need to be able to do something which is uniform and does not take in account constant. So how do people usually do? There is usually a criterion that allows to prove uniform exponential growth. So suppose that there is a number B, so B is a number, such that for every finite generating set, there are two elements in the ball of radius B that generate a free semigroup. Then G is uniform exponential growth. So what does it mean? I give you a number B. Now you choose your favorite generating set, you give it back to me. So I look at the ball of radius B in this generating set, and I must be able to find two elements that generate a free semigroup. If I can do this, if I can find generator of a semigroup fast, efficiently, then I have uniform exponential growth.
This criterion is strictly stronger, right?
Yes. This criterion is strictly stronger. So this implies uniform exponential growth, but it is just one implication, okay? It is a strictly stronger criterion. And this criterion is great, but just to highlight the differences between exponential growth is the following theorem of Minasian and Ozing. So there is an acylindrically hyperbolic group that does not satisfy the criterion. So acylindrical hyperbolic groups were our example of groups that have exponential growth. They have hyperbolically embedded subgroups. They are great, but there exists an acylindrical hyperbolic group that has a sequence generating set in which larger and larger and larger balls contain no element that generate a free semigroup. As Abdul pointed out, this does not imply that such a group has not, so this does not imply that such a group has not uniform exponential growth. Those groups could still possibly have uniform exponential growth. We just don't know. There is no way to either prove it or disprove it, because disprove it is you really need to compute the growth in each generating set and show that those growths go arbitrarily lower. So this is a very hard question. Okay, very good. So this is the motivation. This is what we're going to talk about. And yeah, this is the punchline. Uniform exponential growth is harder. This is what we're going to talk about. And what we want to show today is this. This is the main result. It's a theorem of Caroline Abbott, Thomas Ing, and myself. Let S be a virtually torsion-free, hierarchically hyperbolic group. And now we have an additional hypothesis. Suppose that there is no space E such that G is quasi-isometric to a product where we know that one of the factors is E. Then G has uniform exponential growth. So just to have a quick sanity check, the fact that it's virtually torsion-free implies that this is an infinite group. And the fact that it's not quasi-isometric to this product, in particular, is not quasi-isometric to Z cross a point, so in particularly is not virtually cyclic. Okay, so this is just what those hypotheses are taking care of some trivial examples. Good, but then this is what we want to prove. Okay, other questions? Someone says that virtually torsion-free does not imply infinite. Oh, right, because the trivial group is torsion-free. Sorry, okay, then I guess that, okay, then probably, I think that this is exactly how we state in the paper. So I guess that we are saying something which is strictly speaking wrong, but let's say that let's add infinite. So I always forget that trivial group is infinite. Yeah, I see the question, are there finite hierarchically hyperbolic groups? Yes, all hyperbolic groups are hierarchically hyperbolic and all finite groups are hyperbolic. But those are the trivial examples. You don't need, like this theory tells you absolutely nothing in those cases. Also, the theory of a hyperbolic group tells you absolutely nothing in those cases. They just are there. Very good. So this is the main result. So to prove the main results, we're going to need some ingredients. The first ingredient is a theorem of Durham, Hagen, and Sisto that says the following. Let's use the right one. Let G in G be an infinite order element. Of course, G is a hierarchical hyperbolic group. It's not written, let's just write it. This is a hierarchical hyperbolic group. And let's be an infinite order element. Then the set big G, and this is the definition. So we are defining the set big G to be the set of domain such that the projection on this domain of all the powers of G is unbounded. Okay, this is just a set. Then what do we can say about this set? This set is non-empty. So there is at least one domain inside and contain pairwise orthogonal domains. Okay, so this set exists, is not empty, and all the domains inside are, well, of course, unbounded because they need to have unbounded projections. So and then they need to be pairwise orthogonal. Good. And then what can we say? We can say something more. Moreover, if I have a domain inside the big set of G, then up to a power, G acts on CU loxodromically. So those are two things. G acts. It acts loxodromically and with a lower bound on translation length. Okay. Why G acts on CU? So what could happen? Well, it could happen that the big set of G looks something like this. Is some U1, then U2, then U3, and this just going on forever. And maybe what G could do is that G maps U1 to U2, and then U2 to U3, and then U3 to U4, and so on. But then we can look at the second fact. This is basically from the definition. There is a uniform bound on the number of pairwise orthogonal domains. So this set here is uniformly bounded. So let's say that has some signs n. So up to take the power of g to the n factorial, g has to stabilize. This is just basic combinatorics. G has to stabilize each of those domains. And so this is to say that up to a power g sends u to u. And as you remember by the definition, this means that there is an isometry from cu to cu, i.e. g acts on u. And we are telling that these acts acts loxodromically, and also we have a lower bound on the translation length. Good. Uniform from the choice of G. No, whenever I say uniform, I mean uniform for the whole group. Also, I don't know which uniform you refer to, but I think that all the uniform, so the lower bound is uniform. This is so uniform over G in G, and also this is uniform. Well, the set of, the pairwise orthogonal domain is just a factor of domain. So the domain is defined abstractly,
Davide, I'm a bit confused because it seems like if you have a Morse element, then you won't have any, then big G will not contain any pairwise orthogonal domains, right?
Oh, a single one. It will contain only one.
Okay, because
if
the
it's
statement
only one
says
set,
contain pairwise orthogonal domains.
Yeah, I think that, so maybe the English is strictly speaking wrong, but if I have one like a singleton with one thing, I say that I think that this is a set of pairwise orthogonal domain because there are no pairs.
Thanks.
So, but yeah, that's a good point. So this can be only one element. If there is more than one, they are orthogonal. This is what he's saying. Okay, good. So those are the ingredients we are going to need. And so here is the sketch of the proof. Okay, so this is basically what we are going to do for the rest of this talk. So the sketch of the proof. First, something that is important is that, so we assumed that G is virtually torsion-free. Torsion-free. So this means that there is some finite index subgroup H, which is torsion-free. So this is just a definition. And then there is some, I don't know, some general fact about growth is that if I have H in G of finite index, this symbol here means finite index. I'm trying to make it popular because people need a symbol for finite index. I don't know from whom I saw this symbol. If G is finite index, if H is finite index in G, and assume that H has uniform exponential growth, then so has G. So G has uniform exponential growth. Okay, maybe I need to say, okay, of course, uniform exponential growth only makes sense to finitely generated groups. So just to make sure, we're always talking about finitely generated groups. Yes. Great. So we can just assume that our group G is torsion-free. Now, if you remember, there were two cases. So we were showing that either G is a product or is quasi-isometric to a product where one of the factor is as head, or G has uniform exponential growth. So our strategy is going to be the following. We are going to fix a generating set. And the generating set is going to be called X. And then we are going to show either something happens that allows us to conclude the product. And this part we don't do. We are not going to do. There is definitely no time, and this is somehow harder. Or we're going to show that if what eventually will lead to a product does not happen, then we can find a free semigroup, actually a free group, a free subgroup fast. So this is what we will do. Okay, and actually the lemma that we want to get, and this is going to be the key lemma, this is going to be the end, is the following, is that if, yeah, let's write it here. So this is the key lemma that we need to prove to the end, is that if I have two elements, A and B, such that there is U inside the big set of A, and there is V inside the big set of B, such that U is transverse to V, then there exists a uniform, and this uniform means that does not depend on the generating set, does not depend on A or B. There exists a uniform M, such that the subgroup generated by A to the M and B to the M is free. Okay, so this is our end lemma. And the first bit is going to be showing that we can get to this situation, and the second bit is going to prove it. Okay, also, I notice that I write U and V very similarly. So if I'm trying very hard not to, but if I write U and V very similarly, please stop me, and I will try to make it clearer. Okay, so what do we do? Well, we need to get into this lemma. We need to find element A and B, and so of course we need to find A and B. They need to be short. They need to be short, so that if A and B are short, then A to the M and B to the M are also short. So we need to control the length of A and B, and we need to find U and V inside the big set that are transverse. So, well, let's do the naive thing. So we have a generating set. This is our generating set.
Okay, just sorry, just quickly. So when you say that A and B are short, you want them to be uniformly short.
Yes,
like,
I want.
yeah,
So there needs to be. So short means there needs to be. So I need a uniform. So uniform means that does not depend on A, B, or the generating set. A uniform bound on the length of A and similarly of B with respect of the word length of A and B or B with respect to the generating set X. Okay, this is the word length. Okay.
Thanks.
Good. So we have a generating set. But what do we do? So first, remember we are always thinking torsion free. So the group is torsion free. So every group element has a big set. This is what we needed. So we have a generating set. Then let's define the set curly B to be the union. Let's just do the most simple thing of for the generators of the big set of S, right? So we just take all the generator, we take all the elements in the big set. If we find transverse things, then we are happy. But this would be just way too easy, right? So let's say that we don't find them. So what do we need? We need to get something bigger and bigger and bigger and be able to say that we find either something that is transverse or something that looks like a product. And yeah, so what do we do? So let's take X to the, so let's define, sorry, B bar to be X to the N applied to curly B. What does this mean? So X to the N are all the words of length with respect to the length with respect to the generator X less than N, and B is the set defined before. And N here, I don't want to be any number. I want N to be the bound on pairwise orthogonal domains. Okay? And now two things happen. So this is basically just a combinatorial argument that I will skip. But there is absolutely, if you just think about it a little bit, it's going to be clear. There are two options. So either there are U and V which are not transverse, not orthogonal in B bar, or there are all elements of B bar are pairwise orthogonal. Well, this is obvious, right? So this, what they just wrote is obvious. This is just because one sentence is a negation of the other. But then this is the end bit, and this is just some standard combinatorial, like some combinatorial argument, which is not very hard, that G fixes B bar setwise. Okay. And what's the idea? The idea is that the size of B bar is at most n, and if G would not fix B bar setwise, then it would keep increasing. So I keep applying the generating set, and this would keep increasing, but it cannot increase. So this means that it's just fixing it setwise. Okay, this is the whole argument. And very good. And now, what does this mean? So this means G fix a set of pairwise unbounded domains. Now, this is not a proof at all, but maybe you can see of why now it is not completely unreasonable to think that G has something to do with a product. Okay, so we will not follow that path. That path is kind of technical, but this is what we will not do. So this is will not do. We will follow the first path. So suppose that this is what is going to happen. So assume we found V U not orthogonal inside this B bar. So what does it mean? Well, we have that U is not orthogonal to V, but what are U and V? Let's remind it ourselves. Well, U is by definition G1 times U0, where G1 is some word in x to the n, i.e. is a word of length n, and U0 is in the big set of S for some S generator. Okay, that was the definition of B bar. B bar is we start from B, which is the union of the big set of the union of the big sets of the generator, and then we apply word of length at most n. So this is what U is going to be, and similar V is going to be. Okay, but then what we can conclude? Well, we can conclude that U is in the big set of, okay, now I'm going to write it wrong, I hope it's correct, of G1 S G1 inverse, right? If S is in the big set of U and G1 of U0 and G1 sends U0 to U, by conjugating it, we have that U is in the big set of G1. Okay, let's try to write a proof. This is not going to be extremely formal, but if I do G1, oh no, I screwed up the conjugation, didn't I? Ah, no. G1 S G1 minus 1 of U, and U is nothing but G1 U0. This is G1 of S applied to U0, and this acts loxodromically, and then these just go back to U. And so we are basically just acting on U as in the same way as S acts on U0. Okay, this is not a real proof, but this is somehow something hopefully more or less standard. So what did we conclude? So we conclude that there are words. The first one is going to be G1. Oh, maybe this I should call S1. S1, G1, S1, G1 inverse, and G2, S2, G2 inverse, such that in the big set of those words, I can find inside U and V, which are not orthogonal. And now this word here and this word here have bounded length, because by construction, this G has length at most n, S has length 1 because it's a generator, and G1 inverse, this is also should be a minus 1, also has length at most n. Okay, very good. So I found two words of uniformly bounded length whose big set contain non-orthogonal elements. So now there are two cases. The first case is U is actually transverse to B, and the second case is U is nested into B. Are there questions? No. So let's go for the first. So now we want to prove the lemma. Okay, so let's state again the lemma. So suppose that we have A and B group elements in some group G, and suppose that there is U inside big A and V inside big B, such that U is orthogonal to V, sorry, U is transverse to V. Then our conclusion is that there exists some M which is uniform, for which A to the M and B to the M generate a free group or free subgroup. How do we do this? So we need to play ping-pong lemma. So we need to do two things. First, we need to recall an axiom, unfortunately, but here is where some more hierarchical hyperbolic group structure comes in. And this is the consistency axiom. The consistency axiom says the following: there exists some K such that for each X in G, so I'm just thinking of G as a Cayley graph. So I'm just thinking of elements of G as points of this space. What happens? And now I take for each X in G and for each U and V transverse, the following holds: the minimum between the distance in U of the projection on U of X and the projection on U of V, or the other one, so the distance in V between the projection on V of X, the projection on U on V, this minimum is small. So this is to say, at least one of those two is small. At least one is small. Okay. So now that we have the axiom, we can define the set on which we are going to play ping pong. So I'm going to define the set YU to be the set of X in G. So again, you think of group element just as points, so just G as a metric space, such that the distance in U between X, and here I really mean the projection, but just to allow me to just write X to not having to keep the projection with me all the time, between X and the projection on U of V is bigger than K. And similarly, we define YV to be the same guy. Let's put it here. So YV is just going to be the projection on V of U. Okay, those are two sets. And now I need to introduce the last constant. So I hope they are going to fit. So we said the translation length of each element of on each big set has a lower bound. So in particular, there exists M such that the translation length of A on CU is at least, what do we need? 3K. And similarly for B. And the point is that this M does not depend on A and B, because the minimal translation length does not depend on A and B or the space. Okay, so you just take the minimal translation length and you just say 3K and divide by the minimal translation length. Okay, that's the power you need to take the integer part. And that's the power you need to raise. Okay, so now are we ready to prove? So what we want to prove, our goal is to show that if I have small x in YU, then the distance in V between B to maybe some T M applied to X and the projection on V of U is bigger than K, i.e. B to the M, maybe some T, sends yu inside yv. Okay, this is what we want to prove. So okay, how do we prove this? Very good. So here is cu, and here is cv. So this whole part here is cu, and this whole part here is cv. So there is going to be, here is the projection of, sorry, wrong, on u of v. Here is the projection on v of u. And then we said that there was this neighborhood of size k. Good. And we have our point x, such that the projection of x, this is really the projection on u of x, is in yu. Okay, this is the assumption that the projection is in yu, so it is outside this neighborhood. Okay, very well. Now let's look at the consistency axiom. The consistency axiom.
Sorry, Sam asks if it should be translation length of a to the m.
Yes. Yes, correct. Thank you very much. Otherwise, yes. Very important. Okay. So I was saying, what I was saying, yes. So if x project here on cu, this is our assumption, so that x projects far away from this row vu, then the consistency axiom says that since the projection of u between x and row vu is bigger than k, then the projection on v between x and row uv is small. So from this, we can conclude that x needs to project, so just write x instead of the projection, inside here in v. But then, there is some commutativity of the diagrams that tells me that the projection of v of b to the m x is the same as the action of b to the m over the projection of v of x. This is what the diagram are commuting. So if now I need to, if I need to know where the projection of b to the mx is on cv, I can just take x and then I act via b to the m, and this goes to some point. But the interesting part is that this distance here needs to be more than 3k. In particular, we conclude that this point does not belong to the k neighborhood of row uv. So this is to say, does not belong to the k neighborhood of row uv means that the distance between this new point, b to the tm applied to x, and row uv is bigger than k. So we just show that is what is written here. The distance between b to the tmk and x and row uv, b to the tmk and x, b to the tmkx and row uv is bigger than k, i.e., we just show that b to the tm moves yu inside yv. So we can apply Pingpong lemma, and we are done. Okay, are there questions? Okay, I like this proof because this proof is actually very simple. So apart of some facts that you had to take as assumptions, nothing really scary is getting in this proof. We just need to really get, so I apologize for having a bit cramped slide, but I wanted to have everything on the same page and they write big. It's really just applying this axiom and really having the correct picture in mind. And so remember, we had two cases. We proved this one, and this was the hard case. This is the easy case. And I will just make a sketch of the easy case. I hope I wrote sketch correctly. Probably did not. Well, fine. The easy case is the following lemma, is that if U, if V is inside U and V is in the big set of some B and U is in the big set of some A, then there exists some uniform power M prime such that A M prime applied to V is transverse to V. And then with an argument similar to what we had before, A M prime, then this one needs to be in the big set of B conjugated by M prime. And so since M prime, this one we want it to be uniform. We just are in the case before, okay? So this, then since, so M prime uniform, well, let's just write uniform, implies case before. And this I'm just going to sketch very briefly. So here is the idea. So this is CQ. And then we have somewhere inside here CV. And this is going to be rho, the projection from V to U. And then the idea is that there exists M prime such that if M prime is large enough, so A to the M prime has big translation length. So when I apply A to the, let's do a better picture. If I apply A to the M prime, rho of A to the M prime V U is far away. And here this is secretly using some other commutativity of some other diagram. So this is C, A to the M prime V. And now I'm going to finish this exercise by having someone else doing the work. So exercise, so this is going to be done by Jacob Russell in the exercise class, which says if V and W are orthogonal to each other and V is nested in some U and W is nested in some U, then the distance in U between the projection on U of V and W is small. So since the distance here in U, since this distance here was big, we conclude that V is not orthogonal to the M prime V. Also, we have that it cannot be nested because the group action preserves nesting, and also you would have some contradiction, so it has to be orthogonal. And now we are in the case of before. So this is really a simple case. This is just telling you if two things have a different projection on the top one, then, well, morally, this here is a hyperbolic space. So this is some sort of tree-like behavior. So there is some sort of tree-like behavior from here to here. So if I can pull them apart, then I'm done. And that's it. And that's really the proof. So we proved. So this concludes the proof of the first, the easier case of a new color, uniform exponential growth. And this is really all that I wanted to tell you for this mini course. I hope that you had some intuition of how you can use all of those axioms and all of those projections of one space onto the other to do something.
Thank you.